So this is the first lecture over chapter 17. So in this chapter we look at how aromatic compounds react. So there's a lot of information in this chapter. It's probably one of the more difficult chapters in this semester. So I think I split this up over 5 different lectures. Okay, so in this first lecture we look at this mechanism called electrophilic aromatic substitution, or EAS. And so first of all, I'll just summarize the different reactions in this chapter, and then we'll look at the mechanisms for each of these, the mechanism for each of these reactions. So the basic recipe is if you take benzene with Br2 and FeBr3, so iron tribromide, then what you get out of this is that's a recipe for putting a bromine on a benzene ring. So basically you lose a hydrogen, put a bromine on, so you make bromobenzene plus HBr. You can do the same thing with chlorine. So the recipe for putting the chlorine on a benzene ring is Cl2 and FeCl3. So again, that will just take a hydrogen off and put a chlorine on, and you make HCl side product. If you want to put a nitro on a ring, so the NO2 again, so if we drew a Lewis structure for NO2, right, that's what the NO2, the nitro group looks like. So if you want to put a nitro on a benzene ring, the recipe is HNO3, so nitric acid and sulfuric acid. If you put a SO3 on a benzene ring, so if we sketched out the Lewis structure for SO3, so it looks like that. So you'd make what's known as a sulfonic acid, and the recipe for that is SO3 and H2SO4. If you want to put an alkyl group on the benzene ring, then some alkyl chloride and aluminum trichloride, so AlCO3. So a specific example, for example, would be if we took benzene and CH3, CH2Cl and AlCl3. Then this will take the alkyl group and attach that to benzene. And again, you lose a hydrogen, so you get HCl as a side product. So that reaction is known as the Friedel-Crafts alkylation. So you can put a ketone on a benzene ring, so similar to a Friedel-Crafts alkylation. Instead of an alkyl halide, you would start with an acid chloride, and AlCl3 is still the catalyst. So again, you lose a hydrogen, so you lose HCl and attach the ketone to the benzene ring instead. And then that's what's known as a Friedel-Crafts acylation. So this can be useful because once you have the ketone on the ring, if you wanted to, maybe you want a ketone, so you're done at this point. But if you could potentially reduce the C double bond O down to a CH2. And so one way to do that, so the recipe for a Clemmensen reduction, it would be use zinc and mercury and hydrochloric acid. And that will take the C double bond O and reduce it all the way down to a CH2, so now you have an alkane on the ring. Or another recipe to do that is to use NH2NH2, that's called hydrazine, which is basically rocket fuel, but it has useful synthetic organic chemistry applications. So hydrazine and KOH, again, will reduce the C double bond O all the way down to a CH2. So we've looked at ways to reduce C double bond O's before, but they would reduce down to an alcohol. This will reduce it all the way down to a CH2. Okay, so those are the part of the reactions in this chapter. That's about half of the reactions in this chapter that we'll look at. But all of these, not not the Wolff-Kirchner and Clemmensen reduction, but the other ones we talked about before that, all follow a very similar mechanism. And so that mechanism, again, is electrophilic aromatic substitution. So after the first few steps to make what's called the electrophile, so electrophile would be something that wants electrons, so it's something that's electron deficient. So after we make the electrophile, then all of the mechanisms are the same for those other reactions. Okay, so let's look at the mechanism. How do you put a bromine on the green? So again, Br2, FeBr3. So in predicting the product is easy, right? You lose HBr and then attach the other bromine to the benzene ring. So the mechanism for how that reaction works. So Br2 reacts with FeBr3. So FeBr3 is a Lewis acid. So if you remember what a Lewis acid is, so a Lewis acid is something that accepts electrons. So we can take one of the bromine atoms and make a bond to iron. So we make that complex, and then that is the electrophile that reacts with benzene. So of course benzene has the 3 double bonds in it, so it's got 6 pi electrons, so it's nucleophilic, and so it's going to react with the electrophile. So what we're going to do is we're going to take one of the pi bonds, we're going to take those 2 electrons and make a bond to bromine, and then this is going to leave, so you're going to have FeBr4 minus as a side, well, it's a side product initially, and then as we'll see later, you get your FeBr3 back at the end of the reaction. Okay, so we took those 2 electrons, made a bond from this carbon to bromine, and so now this carbon here becomes positive. So now that carbon is now electron deficient, so you've made that carbocation intermediate. So if you notice at this stage, you have lost the aromaticity in the benzene ring, because now this carbon, of course, has a hydrogen and a bromine on it, because that carbon had 1 hydrogen to begin with. So now you don't have cyclic conjugation, so now the molecule is no longer aromatic. It would like to re-achieve its aromaticity, and so the way it does that is it loses a hydrogen atom. So we'll take these 2 electrons in the CH bond and use them to remake your benzene ring. So now you've got bromobenzene and H plus that you just lost. So now you re-achieved your aromaticity. And so the H plus that you lost will react with the FeBr4 minus. So Br minus comes off of FeBr3, so you get your FeBr3 back, and you get HBr as a side product. Okay, so you use the FeBr3 to get the reaction going, to make your electrophile, but then you get it back at the end, so FeBr3 is not consumed in the reaction, so that makes it a catalyst. So in theory, you could recover the FeBr3 and use it again, and again, and again. Okay, so these last 2 steps in the mechanism, where benzene reacts with your electrophile to make this intermediate, and then you lose H plus to make your final product. So all of these reactions have those 2 steps in common. Okay, so if we look at the reaction with benzene and with CO2 and FeCl3, or sometimes you see aluminum trichloride used as the catalyst instead. So it's the same fundamental mechanism. So in this case, you put a chlorine on a benzene ring and you lose a molecule of HCl as your side product, and the FeCl3 or AlCl3 is not consumed in the reaction, they're just catalyst. So same basic mechanism, take a lone pair on chlorine, make a bond to iron, and now you have your electrophile, which reacts with benzene. So we're going to take 2 electrons in the benzene, make a bond to chlorine, and then FeCl4 minus comes off. Okay, so now then this carbon would be electron deficient because it doesn't have 4 bonds anymore. And then the last step in the mechanism is, so the hydrogen where the substitution occurs at is the hydrogen that comes off. So take those 2 electrons, remake your benzene ring, Now you have chlorobenzene, and the hydrogen H plus that you lost will react with the FeCl4 minus to make HCl and FeCl3. Of course, what we're interested in is the organic product, the chlorobenzene. Okay, so for putting so anytime you see this reagent with benzene, you should just recognize that's the recipe to make nitrobenzene. So the mechanism, so nitric acid, sulfuric acid, both strong acids, but sulfuric acid is a stronger acid than nitric acid. So what happens first is you protonate nitric acid, and now you have a leaving group. Now you have water on the nitric acid, so H2O leaves, and now you have your electrophile. Right, so now you've made so that has a net +1 charge, right? So nitrogen is now +2 charged. So if you calculate the formal charge on nitrogen, 5 valence minus 3 lines minus 0 non-bonded electrons so nitrogen's +2 charge, and that oxygen's -1 charge. So overall, it's a +1 charged species. So that's your electrophile. So that's what wants electrons. So that's what's going to react with your benzene ring. So now the mechanism is the same. Take 2 electrons from the pi bond. Doesn't matter which pi bond you use, because all of the carbons on benzene are, of course, are equivalent. So you could attach the electrophile to any of the benzene carbons. So if we attach it to this carbon, then this carbon will become electron deficient. So that carbon becomes positive. And then on the last step in the mechanism, lose the hydrogen where the substitution occurred at. Those 2 electrons become a double bond, and you remake benzene, and now you have nitrobenzene. And so what happens to H plus that you lost? Well, the H plus and the HSO4 minus that you created in the first step will reform sulfuric acid. So again, so sulfuric acid then is just a catalyst. It was used in the very first step, right, to get the reaction going, and then you get the sulfuric acid back at the end. Okay, so for the Friedel-Crafts alkylation, again, so anytime you see this, whatever's attached to chlorine, that's going to be what's attached to benzene ring, and then you're going to lose HCl as a side product. So the basic mechanism, so aluminum trichloride, so aluminum is a group 3 element, so it only has 3 valence electrons, right? So that aluminum only has 6 electrons around it, so it's electron deficient, so it can accept electrons, which means then it's a Lewis acid. So it's a very strong Lewis acid. So what happens in this case then, it's going to pull a chlorine atom off, and so you make a carbocation. So that's your electrophile, and you made AlCl4 minus. So now the electrophile reacts with benzene, so now the mechanism is the same. So take 2 electrons in the pi bond, make a bond to the carbocation, and then this carbon is now electron deficient, so carbocation there. And to regain your benzene ring, your aromaticity, you lose the H plus. And then that H plus, of course, reacts with the AlCl4 to pull the chlorine back off to make HCl, and you remake your AlCl3. Okay, so note in the mechanism that you made a carbocation, right? You made a carbocation. So what's the rule? So every time you make a carbocation, you look out for rearrangement. So this particular carbocation that we made in this example, of course, can't rearrange to anything more stable, but in this next example is used to illustrate carbocation rearrangement, which will give you a different product. So you can't just take this and stick it on benzene at that carbon, right? Because it's going to rearrange. So if we work through the mechanism, so AlCl3 pulls off the chlorine, and you make that carbocation and AlCl4 minus, and then that's going to undergo a 1,2-methyl shift. So now you have that carbocation, so that's the carbon that you attach to the benzene ring. All right, so now we would take 2 electrons from the pi system and make a bond to that carbocation carbon. And then lose a hydrogen. So again, the hydrogen where the substitution occurred at is the hydrogen that comes off. So lose that hydrogen. And again, it doesn't matter which of the carbons we attached it to. Is that right? Yes. That's not right. Let's try again. That would be your major organic product, right? So not so you would make some of that, but that would be the minor product, and this would be your major organic product, which you only recognize if you remember the carbocation rearrangement. Oh, sorry, there's the mechanism there. I'd already had it sketched out for you. All right, so chlorine leaves, and then the methyl group moves, and then you take 2 electrons on benzene, and then you lose the hydrogen, and there's your product. So again, anytime you make carbocations, never forget that they rearrange. Okay, so the Friedel-Crafts acylation. So it's a similar mechanism. So AlCO3 pulls off the chlorine, and you make an acyl carbocation. So the C double bond O is called an acyl group. And so what's significant about this is that the acyl carbocation does not rearrange. It's a fairly stable carbocation. Right? Why is it so stable? Because it's resonance stabilized. So that carbon's electron deficient, but the oxygen has a lone pair of electrons that you can use to make a triple bond between the carbon and oxygen. And so now the octet rule is satisfied on carbon, and the charge is delocalized to oxygen, and so that stabilizes the carbocation. So putting the carbocation on that carbon with the double bond to oxygen is a decent place to put a carbocation, so it's not going to rearrange. Okay, so then the mechanism is the same at this point. So take 2 electrons from benzene, make a bond to that carbon, and then lose a hydrogen. Remake benzene, and the H plus that comes off reacts with the AlCl4 to give HCl and the AlCl3 back, and you've made an aromatic ketone now. So if you want to make an aromatic ketone, that's the way to do it, by doing a Friedel-Crafts acylation, and you don't have to worry about rearrangement in the process. Now, so you could use this to your advantage if you wanted to make an alkyl benzene without rearrangement, because all you would need to do then is now reduce the C double bond O, and you've got the alkane group on the benzene ring without rearranging the carbon structure. So for example, if you wanted to take benzene and make butylbenzene, well, you could not do this. You could not do a Friedel-Crafts alkylation. Why not? Because this carbocation that you make would undergo a rearrangement, and so then you would attach benzene to this carbon, and you would make the sec-butyl benzene as your major organic product. So if you wanted to make butylbenzene as your major product, then you had to get there by a different pathway. And so this would be the pathway. You could do the Friedel-Crafts acylation first. Right, so take that and attach it to benzene. And then reduce your C double bond O. So you could do the Clemmensen reduction, mercury, zinc, and HCl. And now you've got butylbenzene, or you could do the Wolff-Kishner reduction. And so we won't worry about the mechanisms for those. You should just memorize those reagents and know how to predict the products. But again, they just reduce the C double bond O all the way down to a CH2. And now you've got this straight alkyl chain on there with no possibility for carbocation rearrangement. Okay, so lastly, how do you put the sulfonic acid on a benzene ring? So the recipe again is SO3 and H2SO4. The mechanism, so we can protonate one of the oxygens. Sulfuric acid is strong acid, and then that will give you this electrophile. And now the mechanism is the same. Attach that to benzene. So take 2 electrons from benzene, makes this intermediate where you've lost the aromaticity, and then lose a hydrogen from the carbon where the substitution occurred at, and now you've got the sulfonic acid on your benzene. And then of course the H plus that comes off would react with the HSO4 minus, so you remix sulfuric acid, so sulfuric acid is the catalyst in that reaction. Okay, so we won't look at sulfonic acids very much in this class. What is their utility? You can use them to make a sulfonyl chloride. So this would be a sulfonyl chloride that we've seen before. That sulfonyl chloride is called tosyl chloride. So the reagent that does that, one way would be, we'll see this reagent. Well, we saw that reagent back in the alcohol chapter, if you remember. SOCO2, thionyl chloride. That's one way to convert OHs to chlorine. So that would convert the sulfonic acid to the sulfonyl chloride. And then if you remember back in the alcohol chapter, that can be useful because you can react that with alcohols to make the tosyl group. And then once you have the tosyl group, that'll do an SN2 reaction to displace the tosyl. So you can convert the OH into a good leaving group that way. So whatever good nucleophile you throw in, maybe it's cyanide or azide in this case, N3 minus would come in, kick the tosyl group off, and then you would get this conjugate base of the sulfonic acid as your leaving group. Okay, we'll stop there.